Another DraftScience video. I thought I'd go over some two split explanations, and since this other guy brought up this whatever it is, Arago spot, I figured I would talk on that some. Just as explanation, counter theories of why it happens and what kind of math they're actually using to this most established, most proven, whatever thing. But the only thing that's established is that there exists this probability of interaction. That's it. There's no, I mean, a probability. That how to say this, that there isn't a consistency in terms of how something will react when a photon interacts with an electron. There's not any kind of, it always does exactly the same thing. No, depending on the condition of the electron, it does something different, and that's the creation of a circular kind of, it'll do something different when it's here, and 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 that's the creation of this wave, this frequency. So we know that something rotating has a frequency. You know, it goes from 12 o'clock to 12 o'clock at a frequency. And that's the same as mechanical waves and all kinds of things. That's actually how they create waves, using a rotating device of some kind. I mean, you know, a motor. But anyway, it's just so... the phenomenon exists. That's not being disputed. What's causing the phenomenon is what's being disputed. And there's lots of room for this argument, in my opinion, especially when you see the way they do the math to establish the existence of the wave quality of the photon. So anyway, I just want to talk about this. You know, they did delete this post, and they also deleted some of the comments that had been made by some of these people. You know, so one guy had told the guy who posted the answer, you shouldn't have posted an answer so we could auto-delete. I mean, they were so aggressive to get it deleted. So they've deleted those comments. You know, and they've locked everything after they clean it up, so to speak. I mean, this, you know, it's just so hostile. And you're just saying, why? Why are they this hostile? I mean, they can downrate, they can even put things on hold, and yet they insist, we must delete, we must eliminate, we must destroy, we must stop this. So, like, even though they can substantially just degrade something, make it totally known that this is crap, this is garbage, this is evil, they can put all their labels they want on it. They can tag it, you know, with any kind of label of this is garbage, and that's not good enough. They need to censor it. They need to stop it from being seen. They need to stop it from inciting any conversation, inciting any thought. They need to eradicate it. You know, and you're saying why? Why the extermination policy? Why are they so afraid of leaving some crackpot question available to somebody who would, you know, say, okay, so everybody thinks it's garbage, I'll go read it anyway. I mean, you know what I'm saying? I mean, they can totally label it as nothing, as horrid, as the most disgusting thing ever written on planet Earth, and yet that's not good enough. You got to say why. Why isn't that good enough? Yeah. Yeah. So anyway, they're just religious kooks. So, Emilio Pisanti, John Rennie, Innisfree, it's like Ireland or something, Alfred Centauri, and Dahununu. Fucky Yui. You people suck. Yeah. Anyway, so I will get to my thing here. So anyway, here's this spot thing, and it's basically the inverse of the slit thing. I mean, it's basically just taking a circle. And I like the idea that it's equal distance. So you take a source, a spot source of illumination. You try to make it a spot source. You put a little circle disc to create a shadow, a little round piece of anything, and then you project it on a screen that's let's say, a meter away. So there's a light source. 1 meter away, you put a little disc, and 1 meter away, you have your target. And this is what you get. And if you use different sizes, so big ones give you this, smaller give you this, smallest gives you this. And you can see the wave interference pattern developing. you know, but obviously, but the point thing is created here. You can see a little bit. There's a tiny point of light in the center. So somehow the light is being diffracted to the center. Yes. Yeah, so this is more evidence that light is a wave, because this happens, and you're just like, well, why you draw that conclusion that light somehow is doing something, when obviously what it seems is doing something is the surface the light's coming in contact with. That surfaces have a function that's maybe different than not surface. Next to the surface means something. Unlike throwing a baseball next to a building, okay, where nothing happens, because you can't necessarily throw the baseball really close to the building, right? Yes, in particle physics, something happens, okay? It's different. It's not the same. It's just kind of understanding that the surface of this pen is not a surface. It's not a, some kind of smooth thing. There's there's either an electron right there, or there's a proton right there. I mean, everything carries charge of some kind. I mean, everything carries the product of its character, and charge is a surface phenomenon of the binding of the atomic structure. Clearly, we can induce extra charge, change the charge, but I just mean as a real function. You have to understand that an atom is this nucleus with this orbiting electron, and the electron can have an eccentric orbit. It can be like the Earth. It could be in an ellipse, and it can be a very stretched out ellipse, and the electron can spend a lot of time over here and very little time on this side of, say, a proton and neutron nucleus. And that would create what would be called this polarization, or this idea that there's a charge, and the idea that something encountering that surface at that moment. At one moment there's a charge. At one moment there's a positive. The proton has influence, and in the other rotation, when the electron's on this side, the electron has is dictating the character, what you see. And it's going to be a very different surface depending on whether you're encountering a proton or an electron. Alright, but the rotation of the electrons is really the key. And as I pointed out in the Ising argument, the fact that these things aren't, so if I was to, I'll just do a simple, so here's the nucleus, proton-neutron pair, and you have your electron. What do I want to draw here? Well, what I want to point out is so here's your electron. Let's say it's rotating, and let's put it in an ellipse. The point is it could be doing something quite eccentric, but one would argue that perhaps when it's closest to the proton is when it's straightest, when this line has the least eccentricity in it, and it gets more eccentric out here in the wilderness. The further away it gets, the more erratic, the more possibility for other influence there is. So in a sense, it's although it's moving the same speed, it spends a lot more time over here than it spends over here, merely because over here it's more direct, could have a much straighter alicing, the much less crap in it. And so this, it appears to be moving much faster. It's not really moving faster, it's just going less distance. And over here it's doing a lot more distance. So it could be spending 10 times more time over here than over here in its orbit, merely through alicing, merely through this convoluted path it has to take. So anyway, and that's what I would argue is that creates these diffraction patterns. It depends on where this the electron is in its rotation, and you got to know that it has a direction also. So it's moving this way here, say, and it's moving primarily this way here, and that will have a that'll change whether a photon encountering it it can't be absorbed, let's say, because this is a surface molecule, and the surface molecule is going to have a trouble absorbing a photon because of its electrical balance that has to be maintained, because it doesn't have anything on its other side, locking it to the matrix. There's another word for that. For the grid of the molecular structure. It's weak on one side, right? It's doing a transition with air, an atmosphere. So whenever there's one of these transitions, there's always this tendency to produce ions and loose electrons and lots of things that get on these surfaces. Well, anyway, what do I want to say? Alright, so that's what's happening in terms of the photons are reacting with surface structure, and surface structure is different than other structure. Alright, so in the two-slit experiment, traditionally what they do to do the math is they assume that the photon, let's say it was heading for this slit and it was right here, so it was, let's say, from this margin it was 1 inch away, well, 1 unit of measure and 9 units away from this surface, and they just project another one exactly at the same place in the other slit, so exactly 1 unit away, 9 units away from this other surface. So they just create 2 photons, and then they basically are just calculating for the probability the phase difference that they would end up being here because of the distance difference. So obviously the one further away would travel more distance, it would be out of phase with this one, and they're just using how much of a phase shift there is between the 2 photons, the imaginary one they created and the real one, and defining probability based on that phase difference. So the more the phase difference, the less probable, let's say, the least the phase difference, the more probable. In terms of when they're in phase, they'll have a maximum effect, constructive interference, and when they're completely out of phase, it will not appear anywhere. And that phase difference, again, is just going to be a reflection of how close you are to these surfaces. So, that's part of the math, is how close you are to a surface. So the more likely, so you can sort of understand that if you draw the two-slit again, I could probably just do it with one slit, but it doesn't matter. You could sort of understand that the light going directly through the middle is the least likely to be affected, and the light going closest to these edges is the one that's more likely to be doing this diffracting. So you can sort of understand, if I drew this, let me just draw this picture a second time, for both slits, that you know, the strongest light in the two slit experiments, this is where the strongest light is going right next to this middle impediment. So the strongest light's doing the hardest refracting, and the weakest light is going directly through the middle, and it's ending up creating the... So when you get this two bars in the middle strong, and then it gets weaker and weaker and weaker, what's basically, these two bars are being made out of the light going straight through the furthest from the slit material, and these weaker bars are actually being created by diffractions in both directions from the slits. So the slits are the ones creating, and you can sort of see that here. What's happening in this disc, creating a shadow experiment, is you can see, you can't really, you might not be able to see this as well as me, but there are little lines in here. And so what's basically happening is the light's being, as it goes, so let's just say this shadow was the disc, and you were coming at a disc. The light's hitting that edge, and depending on what it hits, it diffracts either left or right. So it either gets reflected, so to speak, it gets partially absorbed. The atom can't change its energy level because it's a surface atom. So it can't absorb the photon, so then it rejects it. So it grabs it like a, I've analogized it to, you know, it's kind of like a comet could be grabbed by our solar system, held for one orbit, and then released in some direction. So it's not being released in a true angle because of the eccentricity of the fact that it's a surface circumstance. So in the surface circumstance, the reflection is a diffraction. It's absorbing it and releasing it the wrong. Would standard, it would end up getting released theoretically consistent with the direction that it was grabbed in. You know, the same energy goes in, the same energy goes out. And energy the same directional information goes in, the directional information comes out. But if the atom or the electron absorbs any of the directional information through the grabbing process, so if the solar system moves as the object is being absorbed, then it won't leave in exactly the same direction because part of the directional information has been absorbed. It's been it's changed the gravitational matrix of the body it's affecting. It's influenced it, and by influencing it, it can't leave exactly the way it came in because it's absorbed directional information. It's absorbed part of its direction, and so that's creating these diffractions. And what I would argue is the dark line parts, you know, the parts where there's no light, are being created by, again, this Elysing thing, where this, you know, this convoluted stuff is where you're, and 50-50 say percent, this is, or some kind of relationship like that, is where you're getting these you know, these bends at specific locations, and that the 0 points are points where it is spending less time. So there's less probability of encountering an electron in this location, you know, where it's doing this straighter line movement, this tighter directional movement. And so there's no light reflected there because there's no interaction, or the possibility of interaction is diminished. There's no capacity to have an interaction. It might just be directionally effective too, you know. It just might be the fact that there is a point where it's going in the same direction as the light coming in. So you could argue from this point to this point in an orbit, because the light's moving in this direction, there would be no interaction. And it's only when the light's moving, it's moving in some counter direction, more substantially. Um, I don't know the answer. I mean, this is something I'm still thinking about. And at first I was thinking that everything has a I'm sort of trying to explain that everything, even when it has a neutral charge, it has a charge, so to speak, because it's always changing. Because even if you could put all the atoms, if all the atoms had a plus and a minus, we're all polarized substantially, and so it's holding it. The thing would be holding a charge. The back ends of the atoms, so these are the nucleuses that are controlled by the proton, and these would be the electrons. So we would call this a charged body, okay? Minus over here, plus over here, because all the atoms are being distorted. But it's not really all the atoms, it's just the surface ones. But anyway, it doesn't matter. The point would be is that there's still points where the electron is on this side of the atom. It's just that it's lower, it's there less amount of time. So there's still a possibility of something intercountering this and perceiving it as a negative, even though it's substantially positive. But overall, through the more encounters, it's going to be positive more than negative. Yeah. And then the other point I would say is that this does all create these, what are called field lines, and you can have an electric, EMF field. So what you're doing is basically saying that any ions, any stray nucleuses or stray electrons will end up lining up on these field lines. They're not real lines, but they're just lines of magnetic potential. They're lines establishing the fact that once you establish an electrical potential here, you establish it in all these other items too, and their potential kind of creates the fact that they will end up in these separations. So they'll just, it's kind of like the magnet, the filings around a magnet. The filings are creating new little magnets, and those new little magnets are creating the repulsion that's keeping them away from each other. These end up all aligned the right way to be opposite poles, same poles facing same poles. So they're all south on the one side, and the other one has south on the opposite side. So they're repelling each other, and that's what's establishing the voids in between. But you can see that field lines, this looks like field lines. This pattern has every appearance of something that could be created by field lines. So is there anything else I need to say? I guess the most important thing is that if you understand this math of the two-slit experiment and the imaginary second photon they create, to create their math. I mean, come on. The second photon goes exactly in the same location on the second slit. It somehow knows how close to the border, to go. I mean, that's preposterous on its face, right? I mean, if you're going to say that the photon wave was going through both slits, you'd still have to say that there's a presumption, that it's not going to be able to do that. This wave front. Anything else I need to add? So, and then wavelength becomes all specific to this. Like this effect is actually not easy to create. You have to have a very perfect disk, and your light source has to be very point source. So you have to have a light source that's a single point that's projecting out in a cone. That's exactly the size of the disk. So there's a lot of specifics here, and it's also another thing completely dependent on you not using. You using one frequency of light. This one is 633 nanometers. So you have to use, monochromatic light to get these effects, because if you use different frequencies, all these rings will line up in different places, and you just lose this effect entirely. And that is important. At the moment I can't think of why exactly. It clearly has to do with the fact that the electron is going to react differently to different light frequencies depending on its where it is. So in different states, in different proximities to, let's say, the proton, it would have a different capacity to absorb a certain amount of rotational, what's the right word? Its rotational speed will be different. I mean, in the sense that we know that each, well, I'm arguing. See, this is another thing I want to kind of do, is that I was thinking that, instead of attempting to get my entire theory peer-reviewed, that I might just try to get my argument that light is not a single photon, that it's two quantons separated by a distance, and that's what the electron has to absorb. So this is another thing to kind of understand. So what I'm arguing is that there's an electron has a reliable rotation speed around, no matter what its shape, around its nucleus, and it's in a certain position, at a certain time, and then it'll be back at 2x that time, right? I mean 2 times that time. It'll be in that position again 3x that time, and that there's a certain consistency to that. And so what's happening with light is that there has to be a time that the first photon, the first quanton, has to come in, and it's being absorbed because there is gravity here, and so it gets held, it goes around in a rotation, and the second quanton has to show up at the right time in the cycle for the two to be absorbed. For this thing to be able to gravitationally hold it together, this one has to be in the right rotation for this one to be held, for there to be a balance in the overall gravity created inside here, for this one to be also grabbed. And if it doesn't come at the right frequency, there'll be an imbalance, which will mean that this will likely be released. And one could argue, again, based on this kind of conservation principle, that if nothing absorbs any of this directional information, so this came in at this direction, if nothing absorbs it, meaning this doesn't move in some direction, then the same directional information will end up going out. The directional information, like energy, has to be conserved. You can't create or destroy it. Yeah. So, but that's what why frequency would be so critical, is that that it's going to change based on the rotation of these electrons, the speed of their orbits, or the speed of their internal function. Even the electrons themselves are built out of this mechanism, and they're just not capable of absorbing a photon or holding it unless it's the right frequency to match its, say, spin frequency. You could argue. I don't want to mix subjects. Spin gets into a whole bunch of other complicated stuff. So anyway, I'll just say it again, key features are the double slit. The key point to recognize is that the most intense light, so in the single slit, the most intense light goes through the slits where it has the least likelihood of interaction with a surface. And in the double slit experiment, the most intense light has the highest probability of interaction with a surface. That's the key difference between the two, and the diffraction patterns have a, let's say, 9 times difference. So in the single slit, the diffraction pattern is 9 times weaker in terms of its intensity, light intensity, 9 times weaker than it is in the double slit. That's the difference between the two diffraction patterns, and I'm arguing that that 9 times is merely a reflection of the fact that here the most intense light is 9 times stronger than the weakest light. So what I'm saying is the cone of light is 9 times stronger here in the center than it is here at the edge. So that's all that's creating the difference between the two slit and the single slit diffraction, is the fact that the light is 9 times stronger that's encountering the surfaces and being diffracted left and right. So so when you see that bar pattern, the irony is in the two slit experiment that all the bars to the left and the right are being created by the light going closest to the center. So the center light is doing all the diffracting, and it is the periphery light that's going straight through and creating the two primaries. So the primary and the two secondaries are being created by the light being unmolested, and the bar pattern is being created by diffraction of the most intense light, and it's being diffracted in both directions. It's diffracting left and right. Alright, I think that's enough. Mostly. It diffracts unevenly. I'll concede that. Each slit will diffract more light left, or right. So it'll either, whatever side the surface is on. So the left surface diffracts more light that way, and the right surface diffracts more light that way, and less light that way. Well, it's the opposite. You can see it in this point. The fact that this point is so small, because this is maximizing the left-right convergence right here. And so what I get is a single little tiny dot that actually goes around, that gets diffracted that way. And as you make it smaller and get into more intense light, you see that dot gets brighter and brighter. Yeah. So when you're giving it the bare minimum amount of light, you get this little tiny dot. So there's barely any light hitting, that very edge that can get all the way around. It's the weakest light. So your light cone is exactly the same size as your thing. And as the light cone gets bigger than your thing, that's when you start getting this funkiness happening. So they didn't change the light source, they just changed the size of the thing. So for the difference between this image and this image is that this image, the light barely is making it to this edge, and in this image it's going over the edge, and in this image it's going way over the edge. Yeah. Alright. I believe. So anyway, until next time. And such. So yeah, I guess I have to try to find the, there's lots of stuff in this math. And the key thing is to find out where they have the, see, there's this 1 to 16 number. See, this also came up right here, right? 16 millimeters. So it's kind of, this image ends up being 16 millimeters for this 1 millimeter size here at a distance of 1 meter. And you're saying there's that relationship again, the Feynman, the Newton glass experiment, where you have this, the highest probability is, 16%, and the lowest probability is 0. And that if you were to shoot all flavors of light, you'd end up with a 4%. So 4% is really made up of 16 and 0 to get to 4%. So the 16% thing only happens, obviously, 1/4 of the time. Yeah, the 0 only happens 1/4 of the time, and the other two are happening 1/8 of the time to end up with an average of 4 of the time, something like that. So, but see, so that's more stuff I have to get into. But that's all this is made out of. That's all this is really saying, is that there's a 16. You're working with a probability that is, like, I don't know how to, that this, it's not 16 states, but I mean, you're just saying that there's a probability. It's like the electron, where it is in its orbit, it would only be in this part of its orbit 1/16th of the time. It would be in this part of its orbit 16% of the time, and be in this part 84% of the time. That kind of thing. And you can just slice it up as you go across equal quarter increments. You'd end up with those kind of proportions. Something like 0% chance of interaction, 4%, 8%, 16%. Anyway, enough. I guess it's 8, 8, and then 16. It doesn't really matter. It ends up being 4 in the end. When you add them all up. It's just light being disturbed by interaction with surface molecules, which really is surface electrons, which are not the same as internal electrons, let's just say. Alright, enough said. Till next time.